Hi, everyone. My name is Taron Foxworth, and I'm going to talk about Tensorflow and a little bit about IoT, which is super awesome because I play a bunch with hardware because I work for a company called Losant, and it's an IoT platform. So these badges got me really giddy. I can't wait to go, and I'm actually going to that workshop. Super cool badges, awesome conference. So the whole entire goal of my talk is I wanted to see if I can predict if a machine would fail. And this is kind of a big, audacious task. It wasn't something that I particularly wanted to do, but I found it very interesting because there we go. So in IoT, we kind of follow this life cycle. This is a slide deck that one of my colleagues put together. I thought it was so awesome, so I included it in my talk. The way it works is that we generate data, collect it, analyze, react, and then predict. That's kind of like the process that every single IoT application would eventually follow. And along the way is, as you go up the cycle, the value goes up a ton. Because here, like if you imagine a factory floor, for example. If they can predict before the factory stops, then that saves them a ton of money. So they want to implement this, and they want to implement this now. The problem is that if we had to map where everyone was on the life cycle, everyone wants to be at 5. Everyone wants to be predicting, but most of the companies that we work with are between 1 and 2. They're maybe generating some data. Almost all of them are, because most of the machines and factories are generating data in some way. But the data may not be in the cloud or in a proper warehouse, and there's so many edge cases. But all of this goes around this topic of predictive maintenance. And predictive maintenance is kind of like the buzzword in the industrial space right now, because they all want to figure this out, because as you saw, you go up the value chain. When you get predicting, it is just super valuable for them. So predictive maintenance. So predictive maintenance is identifying the predictors of a future failure. So there's no magic here. So what I want to do in my talk is kind of like peel back all the magic layers between like all the IoT, all the machine learning, and all the stuff. So predictive maintenance is all about identifying the predictors of a future failure. And this does not necessarily have to include machine learning, even though I'm going to talk about that in my talk. The cool thing here is these predictors can be simple heuristics. So for example, let's say that anytime I give a bad talk, I fudge the first slide. That's a good indicator that my talk's going to be bad if I fudge the first slide. But if I actually don't do it, it's a good talk. That indicator, so if I fudge the first slide, it's a good indicator of future failure. Has nothing to do with machine learning, but I know that if I'm giving a talk and I mess up the first slide, I'm probably going to mess up the entire talk. So there you are. I predicted the future with no machine learning. So in my research, I figured out, okay, what are my methods of predicting? Because we need to know in terms of the factory floor, how can I start to determine if these machines are going to fail or not? So the two most common are sound and vibration. These are awesome because they're non-intrusive, so I can actually just listen to the machine or attach an accelerometer to the outside of the machine. So these are kind of the two common methods because they're machine agnostic. The problem with these are they don't account for the internals of the machine. So the internal, just mechanical engineering, you can't account for that. And also the problem with this is because they're so external, if you try to build a model that works across different machines, it's pretty hard. Or sometimes even for the exact same manufacturer of the same machine, your model could be different. There's so many factors at play. The next method that people typically do is called forecasting. Forecasting is just basically, since most data in IoT is time series, it's predicting, forecasting out in the future what that value may look like. This is super hard because you need a lot of data to make it happen. And as we talked about before, most of the people in those industrial settings don't have this much data to actually get to forecasting. And then simple monitoring. So we talked about no machine learning involved. A cool story that one of the people that we worked with had is they had a pump and they realized that when the RPMs on the pump started fluctuating, that was a really good indicator that this pump will fail eventually. So no machine learning, all they had to do is say, well, if we see a fluctuation, pull that pump out or schedule it for maintenance because there's a good high indicator that something's going to be wrong. See, no machine learning required. So these are all of our methods, our prediction. But for my project, I'm going to stick with vibration. So let's talk a little bit about data collection, like how do you actually get this data to a place that you can start to do machine learning on it. And this is typically what their environment looks like. There's a bunch of sensors and devices. These may be machines, these may be sensors, a whole bunch of things. They're typically reporting Modbus, which is an industrial protocol, to an IoT gateway, which is just like either an on-prem cloud, or it could be anywhere from an on-prem cloud to like a Raspberry Pi. We've seen some crazy things. And then that IoT gateway is communicating MQTT, which is a pub/sub protocol to the cloud. So in my project, here's what happened. So we built this awesome factory demo, and it was vacuum forming and UV curing. It was like kind of just a plastic demo. It didn't actually do anything, but it moved and people liked it at a conference. So it had the two towers, and the one tower was measuring vibration, the other tower was measuring light. So we did something cool. We were setting the amplitude up to the cloud. So when we actually cranked up the vibration, the factory stopped. It was an awesome demo. But we decided to be extra, and we 3D printed these cool little anchors and actually anchored the factory down to the base. But the problem was that at that point, we could no longer detect the vibration as easily. So once we cranked up the vibration, since they were actually just strapped down, it didn't vibrate as much. So we could no longer clearly define what that vibrating too much or vibrating not enough was into machine learning. And throughout the rest of this project, that was me, just sitting there struggling. Where machine learning works, because I spent a lot of time talking about you don't need it. In this case, where it works the best is because it's helping us detect the subtle changes in the vibration. Because vibration analysis, what we were doing is every second we were capturing 1,000 data points, which is not something that you can just look at on a graph and be like, this is it, or automate in some sort of way. So machine learning, that's where the magic bot comes in. We just give it all the data, and it figures out what the differences are, and now we can use that. So the first thing I did was Google how to predict a machine would fail. This was not helpful. I do not recommend doing that. But then what happens is you kind of look up all the machine learning articles, and a lot of like the handwriting examples came up, and then the iris examples came up, which in no way helped me at all because they have nothing to do with industrial machines. So then I turn to Wikipedia, and then you look at all the different methods of how to do machine learning. And again, these are in no way helpful, and I really want to figure out, like, can I do this? Can I solve a problem without a PhD? So I had a really good conversation with someone from the Google DeepMind team, and he was incredibly helpful because I was telling him, like, okay, I'm really struggling trying to figure this out. I just really want to determine, like, is this thing failing? Is it not failing? He gave me really good feedback. He said, all right, just ignore all, like, the statistics, all the math. Even though they're very helpful, just ignore all of it. Think of everything as a tool in your toolbox. So, for example, there's a reason why you use JavaScript. There's a reason why you would use Rust. There's a reason why you use Go. They're all tools in your toolbox, and you use them for different reasons. He's like, that's just the way, like, the different networks and all the statistical methods, that's the same way that they work. They're all just tools in your toolbox, and you pull them out when you need them. And I was like, got it. That makes sense. What I heard was I can ignore most of the stuff and find the stuff that I actually need. So, in this case, as the person who not knowing what to do, Tensorflow. It's like, oh, this is awesome. It's immediately what I pull. And then I found this thing called Karis. Tensorflow is meant to make machine learning super easy. Now, in retrospect, I think it does a great job at that. But as a beginner of this problem, I looked at kind of this TensorFlow model. I'm like, I have no idea what this is. Or what am I changing? Or how does this even translate to me predicting if a machine would fail? So eventually what I did was I found Karis. And Karis is just incredible. It abstracts a lot of the stuff in TensorFlow, and it gives you this very clean and simple API. And I was like, all right, this works better. I can change numbers. Perfect. But then soon, maybe about 6-7 months later, Tensorflow.js was created. And they also implemented the Karis API, which is super nice because now I can do all this in JavaScript. And because I'm a JavaScript person, it makes it super easier for me to build this project. The cool thing about Karis is that it was so good, TensorFlow proper actually just wrote it into the platform. And the JavaScript library implemented a very similar API to Karis. Also, the awesome thing here is that when you look at TensorFlow.js, it's kind of like if you go from the Python world to this one, the API is a mixture between the standard TensorFlow and the Karis. So I actually learned more about TensorFlow once I did this project in Tensorflow.js than previously, because Karis just abstracts way too much, and you're not at that point in TensorFlow. So then, after all the articles, training the model came up. All right. But I had one weird problem, is that I did not know what a model was. And also the problem with all the tutorials that they actually train the model and use the model in line and typically in the same file and never declare what the model actually is. And I'm super happy there was a machine learning talk before mine because we talked a little bit about that. So in the whole time, I'm like, okay, what is this omnis thing called a model? Like, what do I do with it? What shape is it in? What format is it in? I asked some of my colleagues, I'm like, all right, what is this thing called a model? No one could really give me a good answer. So by the end of this talk, you guys will know what a model actually is. But to kind of preface that, it's just a function, which is really nice, because once I kind of abstracted it to this simple concept, just a function, and this function takes very, very specified input and then returns you exact output. So in this case, my input was vibration from my factory, and then the output was good, bad. Back to training. Training decides what about your data matches your features in machine learning, but what about my data actually makes it good or bad? To do this, you have to have a lot of data, and I mean a lot of data. And I didn't know this going in, but in retrospect, data, very important. And then in terms of this case, if I'm predicting that this machine will fail, I need to have off data, running data, and breaking data. I need to have breaking data to actually determine if this machine is breaking, because the model needs to know what that looks like. And unfortunately, you need to have a lot of it. What training is doing is training is looking at my data and determining, okay, this is what makes it off, this is what makes it running, and this is what makes it breaking. For my case, off and running were good, breaking was bad. That's how I kind of split the 0 and 1. But training is deciding what a part of my data is defining my feature. So is the good or the bad? So now, building the model. Again, in my journey, I basically started off with this question of how can I predict if my machine will fail, which is a very qualitative question. It doesn't yield me any results to actually go out and do something. So getting to the right question was super important. I think and for machine learning in general, like if you're not asking the right questions, it's hard to grab the right data or even know what direction to run into or what toolbox to pull out if you're not asking the right question. So my question is can we predict machine failures? But what that ultimately looked like is looking at vibration, can we determine common patterns in failure? Very, very, it's a way better question. And after coming to the right question, it set me off on a path in the right direction. So the thing is that I know since I was doing pattern detection, I was able to look at neural networks that said, okay, which one to go to pattern detection? So convolutional neural networks are really awesome. They're commonly used for images, and what they're doing is they're basically taking, all right, these parts of the images make up this item, and they're classification problems. It works really well for that, and after reading about it, I'm like, okay, this is maybe the one I want to use. The cool thing is that I didn't have to do much work translating the two because vibration data, which is typically X, Y, and Z, looks really similar to image data, which is RGB. So to the model, it doesn't look like it. For me, I just had to make my vibration data look like an image. The cool part is that all the handwriting examples actually became very helpful at this point. So I got to go back and start over from the jump. But just basically the way the network is working is taking each image and kind of transforming it into a smaller layer. And this is how it's identifying what parts of the image are what you are looking for. And I can translate that exactly to vibration because the same way that we saw in my example, it can pick out which part of that vibration actually determined what was breaking or what was running or off. So let's look at some code. So once I got to TensorFlow, this is where things became easy because I know JavaScript, and also I did it in Python, so it's kind of easy translating everything. So first, I need to get the data. And then next, I need to split the data into testing and training. The cool thing is that you need to have these two really separate because I need to train the data on something, and then I need to test my model in some way, shape, or form. The next thing I had to do was create a tensor. This was probably the most challenging part, getting to TensorFlow, because I had to figure out, okay, what a tensor is, 4-dimensional, then you get like a multi-dimensional arrays. Then you get a little complex there. But generally, I think once you get it, it's pretty good from there. So I had to create the tensors, and basically I had all the tensors for X and Y, so test and train. And then I cheated. I had the Python model already created and working, so it was easily translating from my Python model to my JavaScript model. The cool thing here is that at this point, my model is now a module, which I was able to require. So like one of the benefits of using JavaScript at this point. And then training. So to train that, all I had to do was just say, all right, load my data. I can actually look at a summary, and then I can fit the model using my data set, and then evaluate it. Because it's JavaScript, this API was way more familiar to me and way more approachable kind of going in. And also, like I mentioned before, since Tensorflow.js was a mixture between like all the Python JavaScript stuff and the Karis stuff, I was able to learn more about TensorFlow in this process. One gotcha that I had was working with large data sets. Node blew up immediately. So I had to increase the memory limit, but just fun fact. So as I'm training and everything, the very first thing that happened is I got an accuracy of 17%, and I was really sad because I had no idea how to get there. And at the beginning, what it looked like was me changing just numbers in the model to figure it out. But as you learn and you see how the accuracy is changing, and you look deeper into the model, because now I'm basically studying this one tool in my toolbox, not the crazy amount of networks, you get to figure out like how the number of neurons, or in our network, remember the boxes, like how wide or how tall or width your boxes are, you kind of get a sense of, all right, this makes sense. What's cool part, eventually I got like 80%, and I went to one of my colleagues and was like, yeah, I got 80%, it's so good. And he's like, no, that's terrible. I was like, but I got a B. And he's like, not at all. That means that basically you were detected wrong 2 out of 10 times. I'm like, okay, that makes sense. And especially in these kind of environments, if you detect wrong 2 out of 10 times, it's really costly for them. What you want is a prediction that's closer to 100%, which after a tweaking and just kind of like, all right, I'm focusing on this one type of model, this one example, I was able to get that accuracy up to 99%. Super happy about that. And then this is where I hit another roadblock, because all those tutorials and examples, they teach you how to build and train a model, but then I think the whole production step gets missed, because I'm like, all right, well, what do I do with this now? But at this point is when I figured out what the model is. At the end of the day, the model is just a file, which is super awesome, because in this file is encapsulated with, so JSON defines all the layers, and the weights are the weights of the neural network. So at the end of the day, it is a file, which was super comforting to me, because it made a lot of sense, because once I can do a lot with this file. The cool thing about Tensorflow.js is I really love this, and I really hope they keep it this way. In the example, they actually show you how to save the file, which is really approachable, because if you look at any Python example, it's really hard to find an example of them actually saving the model and then doing something with it. But just directly in Tensorflow.js, they're actually saving the model right up front. I really love that, and I was really happy to see that, especially for the library. I did open up the model. It's not helpful, because I was like, oh, I finally get to see what a model is. But because it's a file at the end of the day, now that makes a whole lot of sense in my world, because all right, this is a file. So now I can take this file, I can give this file to someone else. I can take this file and put it on the cloud. I can take this file and make a server out of it. So in this case, what I did was, you can basically require all the TensorFlow stuff. If you guys are familiar with Micro, it's a really cool library to create like small microservices. But then I can require all my stuff, I can just load the model, because it's just a file at this point, and create a little method called prediction, and all it does is takes my data, it turns it into a tensor, something that my model understands, and then I just create a little export function, and this is my entire microservice, minus error handling and all that other good stuff included. This assumes that everything's work. But at this point, now, because it's JavaScript, the cool part is I know how to scale this, I know how to run this, I know what to do with this over if you know you're doing kind of stuff in R and stuff like that. It's super hard to kind of translate to production. But this was easy to translate for me. But there are multiple ways to get this done. So TensorFlow provides this library called TensorFlow Serving. TensorFlow Serving is kind of their own runtime for TensorFlow models. So you basically upload the model and you can use TensorFlow Serving to scale and run. Ultimately, what I wound up doing was using Google Cloud, which was super awesome because you just upload your model and then they just give you an API. So at that point, now I just interface with this model for an API. So I just sent it literally the vibration data over the last second, and then my result was yay, nay. So what I really want to talk about now is how this works in the real world, because mine was just a kind of an example. So a lot of the times is, I know the cloud is awesome and we use the cloud, but a really big thing right now in IoT is edge computing, because if you think about it in this factory, if this model is determining if my machine is failing or not, that round trip to the cloud and back is pretty expensive in terms of like something could severely break within a second. So this model is running locally, either in an on-prem data center or to something like a Pi. And that machine learning model is typically running in a service that I, like the one I created, but just on the edge, within the environment. So that way, if something's going on, everything's local and it works offline. And we can do other things, so we can control, so they can actually process the model and then stop the machine without having to go to the internet and back. So typically in the real world, these do not leave the environment. And also, the industrial community doesn't like the cloud as much as we do. So EdgeWorks just, it fits with their current mindset of the way they organize their network. Some other learnings that I was able to come up with, so training and retraining. I didn't know why it was important to retrain. That I just kind of ignored that whole step. It wasn't in my toolbox at the time until we moved the demo. And then the thing is that once you move it, you change the conditions in which your machine runs. And that's kind of where it gets difficult if from machine to machine, is that if you move this machine, it no longer vibrates the same way. And the subtle changes could completely bork your model. I learned that the hard way because I did all this cool stuff in the office and I moved it and now it doesn't work anymore. Also, you need to retrain because more data. So now after we move it, I basically have to run the factory for a very long time, break it for a very long time, and then collect all that data and then reincorporate that into my model. And because we saw how to deploy it, I basically just update a file. I've had a lot of thinking about, all right, how does this work from a developer to a data scientist model? To be honest, I did not know what a data scientist actually did until this project, but now I know that it's an incredibly hard job, and mass respect to the data scientists out there. But they have a problem where, because the data scientists are doing their work and the developers are doing their work, there's not an easy translation between the two, because in order to get the model to work, you have to do a lot of like data transformations and getting it to work in a way that your model understands, which, say if you're doing this in R and Python and then your web team is all in JavaScript, good luck figuring out what that conversion looks like. But in this case, once I started using JS, it's super easy because now I can actually build this model and then all of my team members, I can just say, here, check it out. And since they know JavaScript, it's very easy for them to follow. And it's also because I can create modules, like NPM modules for the translations of my data. I can hand that to them too, and they don't have to think about anything at that point. Oh, and I stole the slide from Dan. It was a super awesome talk that I saw a while ago. Also, fun fact, speed. That was kind of the first thing that I got. This is my non-official speed test, by the way. I just literally ran the same exact things in both environments. The Python one took about 9 minutes, and the JavaScript one took about 13 minutes on this exact same model. But you got to think about it. It was using my CPU, which is not the recommended way of training a model. And also, I didn't have enough data that you would actually need to really do this kind of project. But because training takes a very long time, but the inference of a model, so actually determining if my machine is good or bad, that's milliseconds. That's super quick. So this is pretty much irrelevant to the kind of project or choosing between Python and JavaScript. Overall, I would definitely choose JavaScript in the day for a bunch of the reasons that we talked about, is that it was an easier path to production. I think that's the most important part, is now if you ask yourself the right question, you find the right tools in your toolbox, you can do all this in JavaScript, and an easier path is hand this over to your web team and deploy and use. Thank you.